Today we are going to deal with a new chapter, that is Unit 9, Coordination Compounds. What do you mean by coordination compounds? This coordination compound, they are the compounds formed mainly by transition elements. So, coordination compound formation is a characteristic of transition elements. Now, what are coordination compounds? They are compounds in which the central metal atom is linked to a number of ions or neutral molecules by coordinate bonds, that is, by donation of lone pair of electrons by these ions or neutral molecules to the central metal atom. So, how comes the name coordination compound? Because the bond between the central metal atom and the ion or neutral molecule is a coordinate bond. What do you mean by coordinate bond? The electron pair is given only by one atom or molecule. Now, example, NiCO 4 times. This is an example for a coordination compound. Now, the central metal atom is nickel. This is the central metal atom. And we know that nickel is a transition element. Now, CO, this is the neutral molecule here. Now, when we discussed the definition of coordination compound, we said the central metal atom is linked to a number of ions or neutral molecule. Now, here CO, the charge is 0, so this is a neutral molecule. And it is linked, the nickel and CO is linked by a coordinate bond. Coordinate bond means the neutral molecule CO is donating electrons to nickel metal. So, this is a coordination compound. Now, let us see what is the meaning of a complex ion. Complex ions. Now, in the example written above, there is no charge above the square bracket, and I told this is a coordination compound. Now, what do you mean by a complex ion? If the coordination compound carries a charge that is either positive or negative, we can call that coordination compound as complex ion. So, a coordination compound can also be defined as those compounds which contain complex ions. For example, FeCN 6 times 4 minus. Now, you can see the charge for this compound is 4 minus. You can call this a coordination compound, or you can also call this as a complex ion. Whereas, you cannot call this NiCO 4 times as a complex ion because that is a neutral compound. There is no charge. So, that can be called only as a coordination compound. So, coordination compounds can also be defined as those compounds which contain complex ions. Now, there are 4 minus charges for this complex ion. It has to be neutralized by 4 plus charges. So, I can neutralize it with potassium. So, since you know the charge of potassium is plus 1. So, how many potassium I need? 4 potassium ions. So, K4 FeCN 6 times. This is a coordination compound in which the charge is neutralized. Now, this is a complex ion, which is also called a coordination compound. So, when you hear the word coordination compound, a coordination compound contains a central metal atom which is linked to a number of ions or neutral molecules by a coordinate bond. That is, here the electron pair, the lone pair of electrons is donated only by the neutral molecule or the ions to the central metal atom. So, that is a coordination compound. Now, here you can see in this example K4FeCN 6 times, we have the metal ion, that is cyanide ion, linked to the metal, that is iron, the central metal atom iron. So, in this case it is not a neutral molecule, we have ion. Usually anions are taken to form the coordinate bond with the central metal atom. Now, next let us see some important terms related to coordination compounds. So, we are going to study the definitions of those terms related to coordination compounds. So, next, terms related to coordination compounds. Now, the first term is coordination entity. Coordination entity. What do you mean by coordination entity? Coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. That is coordination entity. So, coordination entity means a central metal atom which is bonded to a fixed number of ions or molecules. And example, in COCl3 NH3 thrice, this is a coordination entity in which the central atom, that is cobalt, this is cobalt, it is attached to 3 chloride ions and 3 ammonia molecules. So, this is a coordination, this forms a coordination entity, that is a central atom bonded to a fixed number of ions or molecules. We have ion here as chloride ion and we have neutral molecule also ammonia. So, this forms, and it is written inside a square bracket, it forms a coordination entity. Now, another example for coordination entity is NiCO 4 times. This is another coordination entity. Another example is FeCN 6 times 4 minus. This is also a coordination entity because it contains a central metal atom bonded to a ion, Cn minus. Now, the second term is central atom or ion. So, the first term was coordination entity, second term is central atom or ion. Now, in a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it is called the central atom or ion. For example, in the coordination entity NiCl2 H2O 4 times, the central metal atom is nickel. This is the central atom in this coordination entity. Now, another example in FeCN 6 times 4 minus. In this compound, the central atom is iron. In NiCO 4 times, the central atom is nickel. Now, these are central atom. Now, you can call these central atoms as Lewis acids. So, the central atoms can also be called as Lewis acid. Now, what are Lewis acid? Lewis acids are electron pair acceptors. We know that the central atom, they accept electron pair from the ions or neutral molecules bonded to it. So, we can call the central atom as Lewis acid. So, that was the second term, that is central atom or ion. Now, the third term is ligands. Ligands. Now, what are ligands in a coordination compound? The ions or molecules bound to the central atom or ion in the coordination entity are called ligands. And the ligands may be simple ions such as Cl minus, or it can be small molecules such as H2O or NH3, or even larger molecules like ethane 1,2-diamine, or even macromolecules such as proteins. So ligands means the ions or molecules which are bound to the central metal atom. They are called ligands, and the ligands can be small molecules, ions, or even large molecules like proteins. Now you can call ligands as Levy's base. Why are they called Levy's base? Because Levy's base means electron pair donors. They are called Levy's base because they give or they donate electron pair to the central metal atom. Now, for example, in this complex or in this compound, there is NiCl2H2O 4 times. The ligands are, which are the ligands present? It is the chloride ion and H2O. There are 2 chloride ions and 4 H2O molecules. So they are the ligands in the compound NiCl2H2O 4 times, which are linked to the central metal atom. Now let's see the classification of ligands. Now we can classify ligands into different types. So classification of ligands. Now the first classification is Unidentate Ligand. Unidentate ligands. Now, what do you mean by unidentate ligand? When a ligand is bound to a metal ion through a single donor atom, it is called a unidentate ligand. So, unidentate ligand has a single donor atom. Now, example for unidentate ligand is Cl minus. Here, chlorine will donate lone pair of electron to the central metal atom. Now, H2O. We know that oxygen has 2 lone pairs which can be donated. So, only oxygen can donate electron pair to the central atom. Next example is Ammonia Nh3, where we have a lone pair on nitrogen which can be donated. So you can see in all these examples we have only one donor atom. In chloride ion the donor atom is chlorine. In H2O the donor atom is oxygen, only one donor atom. In ammonia the donor atom is nitrogen. Again we have more examples like acetate ion. It's a unidentate ligand, CH3COO minus. Because the donor atom is that O minus. On oxygen there is a lone pair of electron. So next example is CH3COO minus. This is also a unidentate ligand where we have only a single donor atom. Now the next type of ligand is, next classification is B, Didentate Ligands. Didentate ligand. Now what do you mean by a didentate ligand? When a ligand can bind through 2 donor atoms, we call that ligand as a didentate ligand. So how many donor atoms in didentate ligand? There are 2 donor atoms. So 2 donor atoms. Now example for didentate ligand is ethane 1,2-diamine. This is the IUPAC name and the common name is ethylene diamine. Now in coordination compounds, when you write ethane 1,2-diamine, we write it as En. Short form is En. So when you see En in the coordination entity, it means it is ethane 1,2-diamine. Now how will you write the structure of ethane 1,2-diamine? Ethane means we have 2 carbon atoms and amino group is NH2. So the structure of ethane 1,2-diamine is NH2, NH2, CH2, CH2, NH2. This is ethane 1,2-diamine. And you know that there is a lone pair on both nitrogen atoms which can be donated. So since there are 2 donor atoms in ethane 1,2-diamine, we can call it as a didentate ligand. Now the second example for didentate ligand is oxalate ion. You know what is oxalic acid? Oxalic acid is, so second example is oxalate ion. Now oxalate ion formula is C2O4 2-. This is oxalate ion. You know the formula of oxalic acid. What is oxalic acid formula? Oxalic acid is H2C2O4. So oxalate ion is C2O4 2-. Now C2O4 2- is a didentate ligand. Why? Because there are 2 donor atoms in oxalate ion. Now how will you write the structure of oxalate ion? Structure of oxalate ion is written like this: COO minus, COO minus. Oxalic acid is COOH, COOH. This is oxalic acid. Now oxalate ion is CO minus, CO minus. When you write it as a complete structure, we have C double bond O, single bond O minus, C double bond O, single bond O minus. And here on this oxygen, we have a lone pair, both the oxygen atoms. So these lone pairs can be donated to the central atom, and since there are 2 oxygen which can donate electron pairs, we can call oxalate ion as a didentate ligand. So these are the 2 examples for didentate ligand. Didentate ligand means there are 2 donor atoms. And first example is ethane 1,2-diamine, second is oxalate ion. Now the next type of ligand is polydentate ligand. C as polydentate ligand. Polydentate ligand. Now, what do you mean by polydentate ligand? Now, when several donor atoms are present in a ligand, we can call it a polydentate ligand. And example for polydentate ligand. So, polydentate ligand means there are several donor atoms. And example for polydentate ligand is EDTA4-. Now what is the full form of EDTA? EDTA is ethylene diamine tetraacetate ion. It is 4-. Actually this ion comes from ethylene diamine tetraacetic acid, that is EDTA. That is ethylene diamine tetraacetic acid. Now when I write EDTA4-, it is ethylene diamine tetraacetate ion. Now this is an example for polydentate ligand, means it contains several donor atoms. Now let us write the structure of EDTA and find out how many donor atoms are present in EDTA. So the structure of EDTA is ethylene diamine. So we have CH2, CH2, NH2, NH2. Now here ethylene diamine tetraacetate ion. So it is NH2, NH2. This is ethylene diamine. Now it is ethylene diamine tetraacetate ion. So how is the tetraacetate written? By replacing the hydrogen atom with acetate group. So what will be the formula? It will be CH2 COO minus, CH2 COO minus, CH2CO minus. Tetra means 4 CH2CO minus group. Now you can see the lone pair is present on this oxygen. Now again you can see a lone pair on 2 nitrogen atoms. So count and tell how many donor atoms are present in EDTA4 minus. This is 1, 2, 3, 4, 5, 6. So there are 6 donor atoms in EDTA4 minus, which means this is a polydentate ligand, or you can say that this is a hexadentate ligand. Why hexadentate? Because there are 6 donor atoms present in EDTA4 minus. So this is polydentate ligand. Only one example, that is EDTA4 minus. Now the next type of ligand is ambidentate ligand, D. Ambidentate ligand. Now, what do you mean by ambidentate ligand? Ambidentate ligand means ligand which can ligate through 2 different atoms is called ambidentate ligand. So, in a ligand, if there are 2 donor atoms present, it can ligate either through one atom or through other atoms. We call that ligand ambidentate ligand. For example, nitrite ion. Example for this is, now ambidentate ligand can ligate through two different atoms. And example is nitrite ion. Nitrite ion symbol is NO2 minus. It is not NO3 minus, it is NO2 minus, nitrite ion, ITE. Now, nitrite ion is an ambidentate ligand, which means it can ligate through 2 different atoms. Means, you know, in NO2 minus we have a lone pair on nitrogen atom and a lone pair on oxygen atom. So we have 2 different atoms which can ligate to the central metal atom. So when you draw the show the coordinate bond formation with the metal, we can show like this. If the coordinate bond is formed with nitrogen, then the structure, the linkage will be like this. This shows that nitrogen is donating lone pair of electrons to the metal atom. And if the linkage is through oxygen and the linkage is through single bonded oxygen, then we can show O, single bond and double bond O. And it is very clear that the oxygen is donating electron to the metal. Now, here, since the linkage is through nitrogen, we name it as nitrito N. Means nitrite, it is nitrite, NO2 minus. But when you write the IUPAC name, when you study the nomenclature, you will find that that terminal, that last E will be replaced by O. So, when you write in the coordination compound, the name of nitrite, it will be nitrito hyphen N. What is the meaning of hyphen N? Hyphen N shows that the linkage is through nitrogen atom. Now, here you will write it as nitrito hyphen O. What is nitrito hyphen O? This is an ambidentate ligand in which the oxygen donates electron to the metal atom. Okay, so nitrito O. So this is one example for ambidentate ligand, that is nitrite ion. Now the second example is example 2 is thiocyanate ion. Thiocyanate. ion. This is an ambidentate ligand. Now the first symbol of thiocyanate ion is SCN minus. Now the ligand, this is a ligand, ambidentate ligand, where it has two donor atoms. The one donor atom is sulfur and the other is nitrogen. Now if the linkage is through sulfur, how can we show that linkage through sulfur? MSCN. From this it's very clear that sulfur donates electrons to the metal. Now if the linkage is through nitrogen, we can show it as MNCS. Now from this you can see that the linkage, the lone pair of electron is donated by nitrogen to the metal. Now here you call this as, this is SCN is thiocyanate, so you call this as thiocyanate 2. The ligand is called thiocyanate 2. Now this is NCS and here we call this as isothiocyanate 2. Now here when you see the word thiocyanate, it is SCN, isothiocyanate is NCS. So no need to show the linkage, you will not write it as thiocyanate S, thiocyanate N as you wrote for nitrite ion, because NCS is known as, or NCS minus, this is known as isothiocyanate ion. So you can call this as isothiocyanate. I told you when you write the IUPAC name of ligand, the last E is replaced with O, which you will learn under nomenclature for coordination compounds. So this is isothiocyanate and this is thiocyanate. So these are the two examples for ambidentate ligand. Now what do you mean by ambidentate ligand? Ligands which can ligate through different donor, two different atoms is called ambidentate ligand. Now the last type of ligand is chelate ligands. E is chelate ligands. Now what do you mean by a chelate ligand? When a di or polydentate ligand, didentate means two donor atoms, polydentate means several donor atoms, uses its two or more donor atoms to bind a single metal ion in such a way that a 5 or 6 membered ring is formed with the metal ion, then it is called a chelate ligand. And the ring formed is called a chelate ring. And the complex is called chelate complex. So how is a chelate complex formed? When a di or polydentate ligand uses two or more donor atoms to bind to a central atom. In that case means they use, if for example we have ethane 1,2-diamine. Ethane 1,2-diamine is a didentate ligand, and you know both nitrogen can ligate or coordinate to the central atom. If both coordinate at same time to the central atom, in that case we get a ring structure for the coordination compound, and we call that ligand as a chelate ligand, and that complex formed as chelate complex. So whenever you hear the word chelate complex, they have a ring structure and there are more donor atoms that has ligated or that has coordinated with the central metal atom. And the chelate complexes formed, they are more stable complexes than our normal unidentate ligand complex or didentate ligand complexes. Okay, and this effect of forming chelate complexes is called chelating effect. So that is chelate ligand, and for chelate ligand you can write the example as ethane 1,2-diamine, En. I told you the short form for ethane 1,2-diamine is ethane, En. Then next oxalate ion is another example for a chelate ligand. Then AdTA4- is another example. Okay. Now next comes a word called denticity of a ligand. So these are the 5 types of ligands: unidentate, didentate, polydentate, ambidentate and chelate ligands. Now next is a term called denticity of a ligand. Denticity of ligands. Now what do you mean by denticity of a ligand? Denticity of a ligand means the number of coordinating or ligating groups present in a ligand is called denticity of a ligand. So denticity means number of ligating groups in a ligand. For example, what is the denticity of ammonia? It is equal to 1 because there is only one atom which can donate electrons. So its denticity is 1. Now what is the denticity of oxalate ion C2O4 minus? It is equal to 2 because there are 2 donor atoms present. So its denticity is equal to 2. What is the denticity of EDTA4 minus? It is equal to 6 because there are 6 donor atoms. So denticity is equal to 6. So these are the different types of ligands. Okay. Now I have written here a table with the ligand, its charge and the type. Now the first type of ligand is water, charge neutral 0, unidentate. Ammonia 0, unidentate. CO is actually carbon monoxide, but in coordination compounds we name CO as carbonyl, and the charge is 0, type unidentate. Now we have ions like halide ion Cl minus, Br minus, I minus, acetate ion Cn minus and SCN minus, whose charge is -1. They all belong to unidentate ligand, and you can see SCN minus is ambidentate, even Cn minus is also ambidentate ligand. Now fifth one, ethane 1,2-diamine, charge is 0, it's a didentate ligand. Sixth one is oxalate ion, whose charge is -2, again a didentate ligand. The last one we have EDTA4 minus, whose charge is -4, and it's a hexadentate ligand because there are 6 donor atoms. So this is our third term, that is ligand, used to study coordination compound. Now let's see the fourth term used to study coordination compound. So next is number 4. Coordination number. Coordination number. Now what do you mean by coordination number? The coordination number of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. So coordination number means the total number of ligands present in the coordination compound, that is coordination number. For example, what is the coordination number of platinum in PtCl6 2 minus? What is the coordination number of platinum in this compound? It is equal to 6 because the number of ligands is 6, it is Cl6. Now next example, what is the coordination number of nickel in Nh3 4 times 2 plus? The coordination number of nickel in this complex is equal to 4 because there are 4 ligands, 4 ammonia molecules. Now next example is a very important example, you have to note. What is the coordination number of iron in this complex? FeC2O4 thrice 3 minus. Now this is something very important that you have to note. Oxalate ion, the ligand is oxalate ion C2O4 2 minus. Now oxalate ion is a didentate ligand. So when you are asked to find the coordination number, and if there is a didentate ligand, you have to multiply it with 2. And here you can see there are 3 oxalate ions. So 3 into 2, which is equal to 6. So what is the coordination number of iron in this complex? It is equal to 6. How did you get this 6? 3 oxalate ions into 2. Same way we have one more didentate ligand, that is ethane 1,2-diamine. So that also, if it comes as a ligand, to find the coordination number you have to multiply with 2. Now next example is CO En price 3+. Now En is ethane 1,2-diamine, and what is the coordination number of cobalt in this? Again it is equal to 3 into 2, which is equal to 6, because En is a didentate ligand, so we have to multiply with 2 when you find the coordination number. Now the next term that we have to study is number 5. Coordination sphere. Coordination sphere. Now, what do you mean by coordination sphere? The central atom or ion and the ligands attached to it are enclosed in square bracket, and it is collectively termed as coordination sphere. So, whatever is written inside the square bracket is called coordination sphere. We can also call it as coordination entity. Now, I will give one example. K4 FeCN 6 times. Now here you can see that the coordination sphere, is FeCN 6 times. This is a coordination sphere, and FeCN 6 times, the charge is 4 minus. Now this coordination sphere or the complex or the coordination entity, this part is non-ionizable. So you cannot dissociate this into Fe2 plus Cn minus ions. This part, whatever is written inside the square bracket, is non-ionizable. Now which part is ionizable part? This one, K4. So K4 is ionizable. And we call this part, the ionizable part, as counter ion, which is ionizable. So what is written outside the coordination sphere, that is outside the square bracket, they are called the counter ion. So you can see in a coordination compound we have a ionizable part and non-ionizable part. Where is the ionizable part written? It is written outside the square bracket. It will be either written before the square bracket or after the square bracket. Now here it is written before the square bracket, K4. It is ionizable, and K4 dissociates as 4K plus. Now what is written inside the square bracket is non-ionizable, and what is written outside the square bracket, we call that part as counter ion. So counter ions are ionizable and they are written outside the square bracket. Now the next term, the 6th term coming in coordination compound is coordination polyhedron. Coordination polyhedron. Now what do you mean by coordination polyhedron? In the coordination sphere, means inside the square bracket, the ligands are attached to central metal atom in definite directions in space, thereby giving a definite geometry to the complex ion. So we know that the ligands are attached to the central atom in a definite shape, which means the coordination compounds have characteristic shape. The usual shapes given by coordination compounds are octahedral, tetrahedral and square planar. These are the shapes given by coordination compounds. Now the last term, that is number 7, that is homoleptic and heterolyptic complexes. Now what do you mean by homoleptic and heterolyptic complexes? Homolytic complexes means complexes in which a metal is bound to only one kind of donor group is known as homolytic. Example, CONH3 6 times 3 plus. This is homoleptic. Why is this homoleptic? Because there is only one donor group, that is ammonia. Now, heterolyptic complexes means the complexes in which a metal is bound to more than one kind of donor groups. For example for heterolyptic is CONH3 4 times Cl2 plus. This is heteroleptic. Why is this heteroleptic? Because there are two types of donor groups. There are 4 ammonia and 2 chloride ions. So they are heteroleptic complexes. So these are the terms, 7 terms used in the study of coordination compounds. Thank you.